I'm going to combine these actually. All right, so I'm going to say this. I may have already covered some of this a little bit, but electron spin comes from the electron giving or receiving energy or effectively breathing in or out. This half spin results from the consumption and release by the particle. It can be seen clearly on a coordinate system as a single cycle of a sine wave, and it's, as like a single cycle of a sine wave is defined as 2 pi, which is it starts, here and it goes whoop, whoop, or it's the other way. I don't know. You get a full squiggle and you start at 0, you cross over 0, you go down, and then you go back to 0 again, right? Yeah, it goes like this. Although that might be reversed in the camera. Oh well. So this 2 pi being equivalent to a circle or 1 full rotation, a return to consumption, right? So if you graph, this path here is also equal to 1 full circle rotation, in polar coordinates. So, this is basically what's happening with an electron. It first starts at 0, right? And then it, takes in energy or breathes in. Then it stops, right? It pauses again. And then it breathes out and releases energy. Oh, and now I've paused again, right? And then that's 1 full cycle because now I'm breathing in again, taking in more energy. And then I pause, I breathe out. And so it's basically this, that's how I'm relating it. The way we breathe in and out is basically the same way I think an electron takes in and releases energy. It's kind of this back and forth. And that is why we end up with these spin pairs, because this proton is putting out energy and the electron shows up and says, hey, I'd like a bite, basically. But while they're eating, while they're taking in energy, the other one is there, digesting or releasing energy. And then they swap places. And so that's why it's a 2-pair system, and there's always one spin up and one spin down. It's because the proton can handle up to two electrons, because only one of them is consuming at a time. So while one is there to eat, the other one's there, to rest, basically. And then they trade places. One takes in energy, one's releasing energy. One releases energy, and then you get what I'm saying. They balance each other out, so it kind of creates this stability point. And when they're alone, they're easily coerced to move on because they don't have that other electron to kind of hold on to. So there's once they have that electron pair going on, not only is that electron getting energy from the proton, but it's also getting some energy from the electron, right? So it's getting its fill more effectively than it would off on its own. And so it wants to kind of stay in this relationship. It's a good place for it to be because it's getting, the energy it wants at an effective rate, right? And so it kind of wants to stay there. But if it's by itself, if someone else is offering energy down the street, might as well go check it out, right? So it's easier to kind of take that one away because there's no reason to kind of hang out there if you can get a better deal down the street, right? So they move on and they try and match up with some other electron, and they get a better relationship going that way. So that's kind of what's going on there. And neutrons are more of a kind of symbiotic relationship with the protons, where they don't really add energy for the electrons to consume, but they do provide more mass for the protons. And by doing this, that leads to a higher input of energy, because more mass equals more energy. So it increases the amount of energy the proton can produce, and therefore, output to the electrons. So, the neutron is getting some benefit because it is getting a little bit of the proton's energy, but it's adding more mass to the system. So it's providing more than it's taking, whereas the electron's taking more than it's providing. But the whole point of a proton is to provide, so it doesn't really have a problem with that. It's trying to get rid of this energy, so it's trying to bring protons in to take it away, but it only has so much to give. So it's like, listen, once I'm full, I'm full, right? And so that's why we end up with these stable systems, and that's why we only have so many neutrons in the system, is because the neutrons are still taking some of that energy, and you are no longer balanced if you just keep piling on these other things. Because even if it's a small amount, over time, the proton can't produce enough. Even the amount of energy it needs to produce is not sufficiently recuperated by the increase in mass, if I said that correctly. When the mass gets too large in the atom, it starts to put out, too much energy, which forces itself to break apart. So, it may take on maybe the proton has excess energy at the time, so it can take on an extra neutron, or it can take on, mainly extra neutrons, but it can only handle that for so long. Eventually, it spends up its excess energy that it got from outside sources, and what it provides on its own isn't enough. So then it says, all right, you get the boot, and then it sends it out. It says, you gotta scram. And in some of those cases, the neutron says, nah, I like it here. I'll just help you instead. And I'll just be like you, and becomes a proton or something. But when the mass, yeah, I already said that. And the way that we know that, what is it, fusion? Yeah, I think it's fusion. Fusion happens in stars and stuff because of all the energy is there to allow these combinations to happen. So when there's so much excess energy, that allows the proton to take on extra mass, and it can afford to take on this extra mass, and then it creates helium, and helium is another one of those points where it's at a stable level. The amount of flow coming in is equal to the amount of flow. The amount of energy that is produced is sufficient to maintain everyone and make everyone happy with that mass and that distribution. But then that's not necessarily true for all atoms. And so they can keep fusing and keep adding these extra particles, extra protons and neutrons into the system, and creating it larger and larger if they have the sufficient energy at the time. But once they lose that sufficient energy, they have to start releasing some of their excess mass to reduce their cost. Basically, they have to reduce their spending in order to afford their size and keep themselves together. And so that's why we get this radioactive decay over time, is we have to keep ejecting, energy as we can no longer, sustain it. So it just keeps kind of ejecting it until it reaches a point where it's balanced again. And not all atoms have that balance, but all of the atoms that are most prevalent in our universe as are kind of at those states where they are generally very stable, and it's because they have these equilibrium points where the mass of the system and the amount of protons in the system and the neutrons in the system and the electrons in the system all balances out, and it works. But there's not every atom works like that, so they can only stay in this larger mass state with higher energy until they've spent that energy, and then they decay. And this is not something that's happening crazy fast. It depends on, I guess, how, what kind of demand there is on the atom, and what kind of I guess it depends on the demand and the size, right? So, some things do better than others, but I think everything after lead, or I believe, is considered radioactive or unstable, because at that point it's just too heavy, right? It's too many neutrons. And not enough there's not enough output there to sustain something that large. And it has nothing to do with pressure and pushing out against the pressure pushing in. It's just, we don't have the energy anymore to keep you in here with us, so we're gonna kick you out. So yeah, I think that's pretty much what's going on there. And then I'm going to also add this in now. And then, so that's how it works in a single atom, but then we have molecules that form, and we know that we have molecules that form. And the reason why that is because, we, like I said, we have the electron pairs, right, that work out, and an electron would prefer to pair up with, another person because it's a better deal for the electron, right? But it's also a better deal for the proton, because the proton doesn't change how much it's producing, but it's allowing itself to kind of fill up all available slots in its system. So without having to necessarily increase in size or increase in energy to do it. So, the electron wants a buddy, basically, to kind of give them a better deal. But but they're also getting good service from this proton, right? So if we imagine just hydrogen doesn't really exist by it, just hydrogen, it doesn't exist by itself very commonly. It's more, it shows up as H2, or maybe, I think, really rarely as H3. I don't actually know about that. But I don't know if that makes sense, actually, so probably not. Maybe. I don't know, I'm not a chemist. But H2 is more common because it fills up that pairing, but it allows the hydrogens can kind of create that balance point, because where they're providing energy consistently without ever having to increase the amount of energy that they're producing. Because when it's just one electron, energy is being produced, but the electron's not always consuming it. But once they have a pair, right, then it's always being consumed. That energy is always being taken in. So the most benefits being made. And unless you get excess energy and you bring in, more mass, you're not going to be able to sustain that on your own. But because if you did bring in two electrons, then you would have to feed both at the same time. You can't do that. You can only feed one at a time. And so you need help, right? From your buddy, right? Another proton. And so these pairs form up and fill in these things without having to increase the energy level of the atom itself. And so it kind of fulfills this balance, and it creates a better balance than what they were initially. I think that electron orbitals and kind of the way that they work is it's more of electron clouds, I guess is a better term, but the way that it kind of works is that you have your higher energy electrons on the outside, but they don't it's not like once an electron is in that zone, that energy state, it stays there. I think they're constantly popping around, and the reason why we end up with these probability clouds basically, and there's one area where a majority of the electrons show up is because it's in the middle, right? The majority of them are going to be going down to the nucleus to pick up energy, and then once they have energy, they're going back up to a higher energy state, and then they're kind of bopping up and down, back and forth, depending on how much energy they get. Maybe they get more energy from some outside source, so they hang out at the outside orbital for longer. But they're kind of bopping up and down on these, up and down the line, and there's only so much room in the system, so they have if one that's up high has to wait for an opening down in the level below it, or in a level below it, honestly, not just the level below it, but it has to wait for an opening in the level below it before it can get down there. And I think basically what happens is that these electrons are, it's like filling up at a gas station or something, right? If it's a really busy at this gas station, you're lining up in line, and as soon as you see an opening, you're going over there and boop, you're getting into the slot to fill up. So, even if maybe you don't, maybe if you're still at a half a tank of gas, you may still have a half a tank of gas, but you're gonna go and fill up anyway because, you'll eventually have to fill up. So you're still gonna get into that slot and fill up while you can. And, if the line is long, as soon as you see the opportunity, you're going to want to take it. And so I think that that's kind of what's going on. And in order to do that, it's got the electrons have to kind of expend energy to get themselves past all of the other electrons and their forces. So it has to expend energy to break through the forces of the other electrons in the system. And that is what we see as this radiation of visible light. And that's why we get these distinct lines for different atoms, because the energy that needs to be exerted varies depending on how far the electron's jumping, right? How far it wants to penetrate through other electrons basically fields, and how far that necessarily is depending on the size of the atom. And so I think a majority are, in the center area, because that's where, it's easiest to get down to get more energy, right? And, the majority of them are not hanging out right down there, because if they did, they would fill up on energy. But once they fill up on energy, they're not going to just hang around there, right? You don't just sit at the gas station all day with a full tank. You go and drive places. But so there's not a lot right next to the nucleus, and there's not a lot far away from the nucleus, because if you drive too far away, you better make sure you can get back, or you're going to run out of gas, right? You're going to have someone fill you up, give you some gas so that you can, continue driving. Or, you got to find a new gas station, right? Maybe the other gas station's too hard to get to. You don't have enough gas to get back and refill, so you're pulling over at the next gas station that comes by. And that's why, the valence ones are popping off. They're like, I'm not going to make it back. So we get this higher probability in the middle, mainly because that's just the easiest place for them to be. And, they're constantly moving. They're not locked in these places. It's just that the most movement happens in the middle, which from a probabilistic standpoint just makes sense. And there's certain points we get these kind of clouds of probability, because those in-between points, it's not that they can't exist there, it's just that those are the areas where the fields of the other electrons are strongest, and so it's less likely that an electron will be in that area, because it's hard for it to stay in that area for any given time because of the energy it has to exert to stay there, right? So there's these certain points, and it can only get to areas where there's openings, right? Because if it tries to jump down to a lower orbital, but there's no opening, there's nowhere for it to go. It just gets shot right out. It doesn't matter how much. Maybe I don't know for certain, but maybe it could pop down there, shoot off some energy, and kick an electron out. But I don't know. I think that's pretty much what's going on inside the nucleus. Inside the nucleus, inside an atom, what the electrons are doing. And I guess I can expand this a little bit further. When the electrons are, breathing in or breathing out, we call these things spin up or spin down, because the magnetic field that they would put off doing this, right? Because this is based off of which direction radiation is going. So when it's consuming, radiation is coming in, it's absorbing radiation. And so the magnetic field that forms from that would be the exact opposite of a magnetic field when it is releasing energy, right? Which would be going out. And so what does a magnetic field create? Angular momentum. And so when we observe these particles, right, we're like, oh my gosh, they're spinning, except they're not spinning. And that's exactly right. They're not spinning. It's this magnetic field that's being created by their radiating out and, absorbing in of basically photons or radiation. And that's how we get these different spins and these this kind of reaction that's happening, and that's what's forming that repulsive barrier inside of the clouds that's making it hard for the electrons to be in certain states, because that's where all of their forces are kind of, we have like, we know there's interference patterns basically. And so the point at which the magnetic field of all the cumulative radiation of electrons is at its maximum is in these like gaps in the orbital clouds. And so the electrons don't hang out there because, you wouldn't go hop into, you wouldn't go out into the desert just to chill for no reason, right? It's not necessarily a pleasant experience to be in the hot baking sun on scorching sands, right? That's not fun. Or, I mean, maybe that's not the best analogy. Maybe a better analogy is like, you wouldn't go to the gym and then just get on a bench, right? And, you never complete one rep. You just hold the weight there, right? You're just holding the weight. And that would basically be like you're constantly exerting energy, but you're not actually doing anything with that exertion, right? You're just holding the weight. That would kind of be a better probably approximation of what the reason is why electrons don't hang out there, because it's a waste of energy. Why am I going to just sit here and hold this weight? I'd rather stay where it's easy and I don't have to, overexert myself. And so that's why I think we end up with orbitals, and that's why I think that the orbitals that we call the higher energy orbitals, the outside ones, but I think that's not necessarily because, they like that orbital in itself is higher energy. It's just that the electrons that go there have to have higher energy, because if they don't have high enough energy, they can't get back. And so that's why the higher energy electrons end up on the outside. It's just because that's the only place they can go. Or like not necessarily that's the only place they can go, but they can go there because they have high energy, so they do, but only they can go there and get back. So I think that's everything I wanted to say about that one in this one. So, yeah. Peace out.